So in this video on electric fields, this is the first part, we're going to be defining the electric field strength, looking at field line patterns, defining Coulomb's law, and comparing electric and gravitational fields. Make sure that you remember to use the pause button, make summary notes as you go through, and bring any questions you have to the next lesson. So first of all, we're going to just check that we've got a clear idea about charge, because charge is what's causing the electric fields around it. So a charge creates an electric field around it. It's measured in coulombs. That has to be with a capital C. You can have positive or negative charges. We know that the charge of an electron is minus 1.6 times 10 to the minus 19 coulombs, and that is where we get our fundamental unit of charge from. So first question, just to check this is making sense, can you calculate the number of electrons needed to make a charge of 1 coulomb? Have a little go at that now and then we'll go through it. So we're going to divide 1 coulomb by the charge of 1 electron, and then we're going to see what we get. And I get, when I put that into the calculator, 6 times 6.25 times 10 to the 18 electrons. So now we've had a little chat about charge and reminded ourselves about what we're already aware of in terms of charge. We can start looking at electric fields. Now you'll see hopefully some similarities between some of the other fields that you've already studied in physics. An electric field is a region of space in which a charge experiences a force due to its charge. And hopefully you can see the similarities in the definition here as well, where we've been defining different fields. We've got different types of field line patterns here. We've got the radial field around a positive point charge, and you can see that the field lines get further apart as the distance from the point charge increases, suggesting that the field strength is decreasing with distance. And we've got the radial field around a negative point charge here, and you can see the key difference is the direction of the arrows on the field lines. The field lines are pointing towards the negative charge and away from the positive charge, okay? And this is telling us about the direction of the force that a charge experiences within an electric field. We've also got the field line pattern here for a hollow charged sphere. And as we've seen in previous fields, we've got the field lines going from the outside of that hollow sphere. We haven't got field lines in the hollow sphere. And we've also got here the field line pattern for a uniform field between two plates that have got opposite charges. So here's our negatively charged plate, here's our positively charged plate, and here are our parallel, equally spaced field lines, and they are at right angles to the surface of the charges. And you can see here we've just got the little curvy ones at the end. Make sure you are happy drawing these field patterns. So maybe pause the video now, draw them all out, check that you can remember all the key points on them. So a couple of really key important points to remember about these field line patterns. First of all, the arrow on the field line is showing the direction of the field. And in our electric fields, we're always going to go from positive charges to negative charges. Second, the electric field lines, are, in terms of drawing them, always are going to be perpendicular to the surface of the conductor, whether that's a point charge and it's a sphere, or whether it's flat plates. The field lines are always going to be perpendicular to the surface. Remember that the closer the field lines are to each other, that's representing a larger electric field strength. So the field line patterns, the diagrams, are giving us information about the strength of the electric field. And we're going to come on to how we quantify electric field strength in a moment. And also remember that if we're looking at a uniform field, we've got equally spaced and parallel field lines showing us that the electric field strength is the same across that field. Okay, right. Let's now have a chat about Coulomb's law and see, when we're going through this definition, if you can spot any parallels with other laws defining fields that we've talked about so far. Coulomb's law states that any 2 point charges exert an electrostatic force on each other that is directly proportional to the product of their charges and inversely proportional to the square of their separation. Now, if we think about writing those words mathematically, we're saying that the force between those two point charges is proportional to the product of their charges. So large Q here would be the charge of one of the charges and little q would be the charge of the other one. So the force is proportional to the product of those charges, but also it's inversely proportional to the square of their separation, so r squared. Now when we put those two together, mathematically, we can say, right, F is equal to a constant multiplied by the product of the charges divided by r squared. So let's have a little look what we can do with that. Now, if we investigate that relationship more, and we plot some graphs and make them straight line graphs, and we find the gradients, etc., etc., just as we always love doing in physics, we can find out more about this constant k. Okay, and it turns out that this constant k is equal to 1 over 4 pi times the permittivity of free space. Now, the permittivity of free space is equal to 8.85 times 10 to the minus 12 force, times 10 to the minus 12. Now, if we change the material between the charges, we are going to change this value. So this is the permittivity of free space. And in our next video, we're going to be talking about permittivity a bit more and how we might need to change that value. This value is available in your formula books. And what this means, if we put this into this equation here, is that we can write Coulomb's law in this format here. So the force is equal to the two charges divided by 4 pi over the permittivity of free space multiplied by r squared. So let's have a little look at electric field strength now. We're going to define it, we're going to look at some equations. So the electric field strength, the force experienced per unit of positive charge at that point in the electric field. So we've got a force per unit charge. When we write that mathematically, we've got F over Q, so force over charge. And we're representing the property electric field strength here with a capital E. And we need to be really careful with using the letter capital E within this topic, because we're going to use it to represent electric field strength, but also a little bit further along you'll see we're using it to represent energy. So you have to be really on top of your equations and know which one's which so that you don't get confused, okay? Just as we saw before, electric field strength is a vector quantity. It's got magnitude and direction. And we are measuring it in newtons per Coulomb. Right, here's a task for you. I want you to compare a gravitational and an electric field, everything that we've talked about so far, okay? So things I want you to think about, what is it that creates the field around it? What type of field is it? Are there expressions for field strength? How does the field strength vary? What type of force is there between the particles? Which direction does it go in? Can you give me some equations for force strength and field strength? And could you tell me what type of field it is? So pause the video now, have a go at that, have a think about everything we've looked at in our gravitational fields and our electric fields and try and compare them. So hopefully we've come up with something that looks a little bit like this. In terms of the property that's creating the field, in our gravitational field, it's mass. There is a gravitational field around mass. But in our electric field, it's charge. If you have a point charge, there is an electric field created around that charge. In terms of the type of field produced, this is where it's interesting. So we just saw with the electric field that positive charges repel and negative charges attract. But with the gravitational field, in terms of the direction, it's always attracting. Yeah. In terms of the field strength, we've got some real similarities here. So gravitational field strength is the force per unit mass, and the electric field strength is the force per unit charge. If we look at the force between the particles, we can see some similarities again. It's proportional to the product of the masses, as well as being proportional to the product of the charges, and it's proportional to 1 over the separation squared. So that's the same with both fields. If we now write some equations for the force strength and the field strength for these different fields, we can see we've got Newton's law of gravitation here, yeah? So universal gravitational constant times the product of the masses over r squared. In our electric field, the force is equal to the product of the masses over r squared, and we've got our constant in here. And then in terms of field strength, we've got gravitational field strength is equal to our constant multiplied by the mass of the point mass over r squared. And in our electric field, it's equal to our constant multiplied by the mass of the charge of the test charge over r squared. So some real similarities in those equations, and hopefully you're seeing those relationships more clearly. And then finally, in terms of the type of field, with both of them, we've got point masses and point charges producing radial field patterns. So within this video, just to recap, we've looked at field line patterns, we've defined Coulomb's law, we've defined the electric field strength, and we've compared electric and gravitational fields. Make sure you've made your summary notes, bring any questions to the next lesson, and look forward to the next part on part 2 of electric fields.